Francis and I go a long way back. I think we've known each other for at least 25, perhaps even 30 years. I was Francis's PhD student at the Vrije Universiteit Brussels, the Flemish or Dutch-speaking sister university of the Université Libre de Bruxelles. Francis is a Belgian cybernetician who investigates the emergence and evolution of intelligent organizations. He presently works as a research professor at the Vrije Universiteit Brussels, where he directs the transdisciplinary research group on evolution, complexity, and cognition, and also the Global Brain Institute. He's best known for his work on the Principia Cybernetica project, his model of the internet as a global brain, which I mentioned in my talk yesterday, and his contributions to the theories of memetics and self-organization. So again, it's my pleasure to welcome Francis Heylighen to the stage. And Francis will speak for about 30 minutes, and then we'll have David Napier and Steen Rasmussen add their comments. Take it away, Francis.
Okay. My talk is Emergence and Self-Organization. Just like our session, these are two words that are used a lot, especially in complex systems theory, but that are rarely well understood and that usually people tend to see as something very difficult or at least mysterious. So what I want to do here is to take a little bit away of the mystery of these terms and show that actually emergence and self-organization are very, as I call them, simple, natural, and common processes. So let's start by contrasting the complexity science with the more traditional science that we would call reductionist science. So reductionist science says if you have some complex system and you want to understand it, then you can only do that by analyzing it. That means to cut it up into the different components. And these components, if they're still too complex, you cut them up further into smaller components, and if these are still too complex, you cut them up further and up to the level where you end with elementary particles. So the assumption of this kind of science is reduction. That means you reduce the whole to its parts. Whatever the parts do, that's also what the whole will do. So you can't say that wholes have something more than parts. So the concept of emergence in reductionist philosophy is either an illusion, that means we're imagining that there is something emergent, but actually there isn't, or it's a mystery, something that we can't quite explain scientifically. So what I want to do is to argue that it is not like that. So against reductionism, commonly, we oppose holism. Holism is looking at wholes rather than at parts. And very simply put, the idea comes from Aristotle. What we speak about a whole, we say that the whole is more than the sum of the parts. But saying that something is more than, it implies that something is added to the parts that was not there yet in the parts. So for me, it's very simple. What the whole has more than the parts are what I call the emergent properties. So the emergent properties are simply these properties of the whole, which I cannot reduce to the properties of the parts. That means properties that I cannot explain by just looking at the properties of the parts. So emergence is typically something novel arising at a higher level of complexity, and what we call novelty, we're speaking about creativity, we're speaking about something that is really unexpected. So emergence is what we need if we want to show, to explain how something really novel emerges, whether it's origins of life, origins of language, origins of consciousness, origins of society. All of these are examples of emergence. Of course, very difficult, very complicated parts of emergence, but what I want to show is that the essence of emergence in se is simple. So let me just give you some examples of emergent properties to show you how simple the definition is. So if something can be explained as being merely the sum of the properties of the parts, then it's not emergent. So suppose that I look at a car as a complex system. If I want to know the weight of the car, well, I just need to add the weight of all the different components of the car. So weight is not an emergent property. On the other hand, if I look in a catalog about deciding which car I'm going to buy, I may be interested in the weight, but probably I'm more interested in things like the maximum speed of the car. Now, the maximum speed is an emergent property because simply none of the components of the car has a maximum speed. A tire does not have a maximum speed. A motor engine does not have a maximum speed. A seat does not have a maximum speed. It's only when I put all these components together in the right way that I can say what I have now is a car and that has a certain property that I call maximum speed. Let's look at the material like, for example, iron. That material is made up of atoms. So if I want to have the total mass, the total weight, or the total number of atoms, well, they're just the sum of the atoms individually. But now if I look at that material, that will have properties such as temperature, color, hardness. These properties are not properties of the atoms. Atoms don't have hardness, atoms don't have temperature, atoms don't have color. And yet, a last example, when I speak about music, I can look at all the different notes that the different instruments are playing. If I want to know the loudness of the music, well, it will be the loudness of all these instruments playing, so it's a sum. But of course, that's not what interests me in music. What interests me in music is the melody, the rhythm, the harmony, and these are emergent properties because individual notes do not have melody, do not have rhythm, do not have harmony. So I'm speaking about properties, but first I need to give you a definition of property, a definition that can be scientifically operationalized. So properties in science are things that you can observe, that you can measure by doing certain experiments. And what is the most generic type of experiment that you do to see whether a system has a particular property? You challenge the system by giving it something that in psychology is called a stimulus, or what more generally is called an input. And then you see what comes back, what is the response of the system, what is its output. And the relationship between the two, that's what I call the property. So the property for me is, given an input A, the system gives me an output B, that defines the property. Now, some properties are fixed, that means the system always has that property, and some properties can be variable, that means it depends on the state of the system. The speed of the car is variable, it can drive fast or it can drive slow, but the color of the car is fixed, it normally does not change. So, to make that concrete, I'll give you an example of a very simple property of color. How do I know that, for example, a billiard ball has the color red? Well, you might say, well, I just look at it, but no, you can't just look at it. In order to look at it, there must be light, and that light should be white light if you want to see the real color of the billiard ball. And then what you see is that the white light that you direct at the billiard ball is reflected, but now only in the red frequency range. A variable property of that same ball could be the momentum of that ball. How do you measure momentum in physics? Well, you let the thing bump into a weight of which you know the given mass, and then you see how much has this bump, this collision with the billiard ball, speeded up the mass, and that defines your momentum. So each case, there is an input, you let the ball hit a mass, and there is an output, you measure how the mass has changed in velocity. So these are properties in general. Now I'm interested in emergent properties. So first let me define a whole. A whole is a network of systems that are coupled. That means there are components, but the components are not independent the way that grains of sand are in sand. The components are coupled. What does it mean, coupled? It means that some of the output of the one becomes input of the other, and vice versa. Coupled system, when something happens to the one, others are also affected. So that means I defined properties as input-output relations. I know the input-output relations for a single component. Now, if I couple these components in a network, it's kind of obvious that the input-output relations for the network will be different because I give an input to some of the components in the network. These components pass on that input to others, pass them on to others. The whole thing starts maybe propagating throughout the system, and at the end there is a reaction, and that is on the output. Let me stay with my simple example of the color. So suppose that I have, instead of a system that is a red billiard ball, I have two systems. I have a red billiard ball, and I have after that, a yellow. Let's say I have a yellow ball, and I have a blue filter. Now, if I put the blue filter in front of the yellow ball and I shine light on it, the yellow light that passes through the blue filter will look green. So by just coupling the two systems in this very simple way, the one after the other, I have turned the property of yellow for the ball and blue for the filter into the property green. Now, emergence usually is understood not so much as a property being emergent, but as a property emerging. That means a process where some new property appears that wasn't there. So emergent properties arise when a system arises. That means a whole is formed where there wasn't a whole before. I had, for example, my grains of sand. They were independent components. There was no system there. But now I mix my grains of sand with cement, and now the grains of sand are fixed to each other. They are coupled. And instead of having just loose sand, now maybe I have a brick. I have a system that has completely different properties from the loose sand because I have coupled the components. What does it mean? Coupling the components so as to form a stable whole? Well, I'm assuming that the whole is stable enough so that it has certain stable properties. That means that also the couplings must be stable. It means that once my grains of sand are mixed with the cement, they can no longer move. There is what I call, they are mutually coordinated, they are adapted, they are synergetic. That means there is some kind of a coordination so that whenever something happens to one component, the other components also are involved. Now, stability, that's actually easy to explain as a process. You assume that some system is undergoing variation. That means it's just changing. That's what happens in the world, things change. But some of the configurations are unstable, that means they fall apart. But while the variation continues, sooner or later I will come to a configuration that is stable. And then the principle of natural selection tells me simply, well, it's stable, then it will not fall apart, so it stays. So you just go on varying until you get into a situation where things are stable. Once you have that stable configuration, you have selected the stable whole. Now we come to self-organization, which will explain this process in a little bit more detail. And I will first give you a standard definition of self-organization. And that standard definition says that self-organization is global order emerging out of local interactions. So what does that mean? First order means that I have some coupling between my components. I started with individual components. They were moving independently. Now they are moving in an ordered way. That means there is some kind of a constraint, there is some kind of a coupling, there's some kind of a coherence that has arisen. That means there are stable couplings. Self-organization, why is it self-organizing? Because nobody else is organizing it. There is no outside agent who is telling the system what to do. The appearance of that order is spontaneous. The system will just organize itself. its own dynamics lead to the emergence of this global order. So this is very important as a kind of a philosophical principle, that is that if you see that there is order in the world, that there is organization in the world, you do not need to postulate some designer such as God or some engineer in order to explain why there is organization. Organization can produce itself. So here's a typical example of a self-organized system, a snowflake. But why does this self-organization happen? It's the same principle that I explained, but now we'll go into a little bit more depth. And the principle actually was already formulated a long time ago, namely in 1947 in a paper by the famous cyberneticist and a person I very much admire, W. Ross Ashby. And what Ashby said is that if you take any dynamical system, that means a system that will change following certain rules, then that system will sooner or later settle in a stable configuration. That's just the same principle I just explained. You undergo variation, and as long as it's unstable, you continue varying until you hit on some configuration that's stable, and then by definition you stay in that configuration because it's stable. And the second thing Ashby said is that if you look at that stable configuration, you know the system is stable, and then you look at the components of the system, then you have to assume that these components have mutually adapted, that the one is stably coupled to the others. So if it were not the case that the components were stably coupled, well then the whole system could not be stable, then the whole system would fall apart. So it's actually an extremely simple principle, but it's difficult to argue that it would not apply. So the conclusion that Ashby said is that the principle of self-organization is that any complex system left to its own devices will organize itself in some kind of an order that consists of its components or subsystems being mutually adapted or coordinated. So that stable configuration, nowadays in complexity science, the common term for that is an attractor. An attractor is a region in the state space of the system. So those who know a little bit about dynamical systems know that dynamical systems go to different states. While they vary, they go from one state to another, and they have a typically very large or infinite state space of all the possible states. And within that space, we can distinguish certain regions that we call attractors. And what's an attractor? It's a region that the system can enter, but once it's in the attractor region, it can no longer leave. That's why it's called an attractor. An attractor is a little bit like a black hole. You can get into it, but you can't get out of it. So it does not mean that the system stops moving, because inside the attractor, there are still lots of different spaces. The attractor can be itself infinite. So the system continues moving inside the attractor, but it simply no longer can get out. And these attractors, they are surrounded by what is called an attractor basin. So the basin are all the states in the state space of which the dynamical evolution will lead to the attractor. But once in the attractor, it can't come back. So here on the drawing, you see 3 gray spots that are a bit like lakes. You could imagine it that they are mountain lakes, and you're looking at it from above, and then the arrows show how the system will evolve from a particular state. The arrow shows that from that state it will lead to this attractor, and then you see that there are boundaries between the different basins, depending on which side of the boundary you start. Either you end up in the one attractor or you enter into the other attractor. What we also need to remember is that complex systems have lots of components. That means lots of degrees of freedom. That means they have very highly dimensional state spaces, and that means typically they have also many attractors. And yeah, we don't know a priori what the attractors are, or we don't know a priori in which attractor the system will end up. So Assume that your system has ended up in an attractor. What does that mean? It can no longer go outside the attractor. That means it is constrained in its further variation. Constrained means it has lost degrees of freedom. It can no longer move outside of the attractor. That means that if the system itself consists of different components that could move relative to each other, the loss of degrees of freedom typically means that the component no longer can move freely relative to each other. They have become dependent. There is some kind of a dependency created between the components, and that dependency means that now I will have to typically describe the system using different degrees of freedom, and these different degrees of freedom typically will be emergent because I will have to measure them in a different way. I will get different results if I do input and output experiments on them. Let's go even a bit deeper into what creates the self-organization. When we look at the individual components now, so we assume that we have a system with many different components. Initially, these components can move freely, but they interact. They are somewhere in a space where one component will have some effect on its neighbors. We assume that there are local interactions. To all these local interactions, the components go to different states. They undergo variation until the moment when locally they get into some kind of a local attractor, that means into some kind of a stable coupling, which I call an alignment. It's as if the two components now no longer are opposing each other. They are adapted, mutually adapted, or coupled or aligned. And what then typically happens is that you start locally aligning some of the components, and then the neighbors of these components will also start aligning to their neighbors, and so the alignment propagates throughout the whole system. And we typically see that this is a nonlinear process. That means a process which is self-amplifying. The more components are aligned, the larger the influence they have on the remaining components, and the faster the whole system will self-organize. It's a little bit like some of these experiments where you have a saturated solution of salt, and the salt will start to crystallize somewhere, and you drop just one little crystal somewhere, and then suddenly everything around that small crystal will start also to crystallize, so the crystallization propagates. So eventually, the whole system becomes aligned. Now, I will give you two examples of that I always give in my courses because they are so simple. The first one are materials that get spontaneously magnetized. So these materials consist of what are called spins. Spins are like molecules with a small magnetic field. On the left of the picture, you see that initially all the spins are randomly oriented. But randomly oriented spins will be in a relation of conflict because it's like with magnets. If you put the north and the south pole of two magnets together, they will repel each other. So the different components there, they will tend to move to thermal fluctuations until some of them manage to align. That means point in the same direction. Once they are in the same direction, they are no longer repelling each other. Their potential energy has gone down. And then when a couple of them are aligned, all the rest will align. And in the end, you end up with what you see on the right, all spins pointing in the same direction. The system is organized, it's ordered. Now all of them have the same magnetic field, and now the whole material has become magnetized. That's a very simple example because the end result is that all the components just become static. They are frozen in place, they all point in the same direction. Now, self-organization becomes more interesting when the end result, the attractor, is one in which there is still movement, in which things still happen. So we can also have processes that self-organize. So when I say that systems tend to get coupled in a stable way, that coupling does not need to mean that they get frozen in place. There can be an ongoing flow. That means that energy or materials are still circulating throughout the city, throughout the system. What counts is that you have a dynamical system where flow happens, but the flow is stable, that means coherent, that means self-organized. A typical example of that kind of a tractor is a limit cycle. And that forms what is known as a dissipative structure. A dissipative structure is a self-organized system, but where now there is a flow so that energy is constantly being dissipated. And I'll just give you one example, no, two examples. So the first example, I think everybody has seen already, these are swarms of birds. The birds are moving, of course. If they would stop moving, they would fall out of the sky. They have to move, but at the same time, they move in a way that is aligned with their neighbors. They will always move in such a way that A, they do not bump into the other, so they keep a minimum distance, and B, they move in the same direction as the average of their neighbors. And those simple rules of alignment create these beautiful kind of swarms and flocks, of which I'm sure everybody has seen videos. But I'll end with a last example, which I also like a lot because it's so simple and it illustrates a main point. It's called Rayleigh-Benard convection. And it's an example of self-organization that happens in a liquid. And you assume that your liquid is heated from below. So at the bottom, for example, you have a flat pan in which you put a little bit of oil. You put the pan on the fire, so the bottom of the pan is heated. The top of the liquid is at the air, so it's cooler. So what happens if the liquid is heated from below? Liquid that's heated expands. Expanded liquid becomes lighter, so it tends to rise up. The liquid on top is cooler and therefore heavier, so it tends to go down. But now you have a problem. You have liquid moving up and liquid moving down at the same time, so there is conflict between these two streams. So what happens? Initially, you see that the movements in a liquid are kind of random, but what happens is that they self-organize in the sense that on one particular spot, for example, there we see that on the left you see that all the arrows point up. That means here the flow is moving upward, bringing hot liquid from the bottom to the cold surface. Then at the cold surface, the liquid cools down, it moves to the right. Once it's at the right, it has cooled down enough, it starts sinking again to the bottom. At the bottom, it heats up, it moves to the left, and like that, it forms a cycle. It forms a continuing cycle. Now, what's interesting to note here is that this cycle that I have drawn here is turning clockwise. But there is no reason why it should turn clockwise. It could just as well have turned counterclockwise. That illustrates another aspect of emergence, which is that there are different attractors and you don't know typically in which attractor you will come up. In this case, the attractor could be clockwise, but it could just have been counterclockwise. The two solutions are good forms of self-organization. And finally, I will leave you with a picture of how this Rayleigh-Benard convection looks from above. Here I have shown it from the side, kind of a crosscut. No, this is still the look from the side, but if you look from the top, it creates this beautiful hexagonal pattern where if you look in the larger thing, you see that there is liquid coming up on the white spots and going down in the dark spots. So it creates these patterns that are alignments. So let me finally summarize what I have said. Wholes have emergent properties. That means properties that cannot be reduced to the properties of the parts. But what are properties? Properties are relations between input, what you do to the system, and output, how the system reacts. And because wholes consist of connected components, they have different input-output relations than parts. Therefore, they have properties that the parts do not have. Where do these wholes come from? These wholes are formed to self-organization. Self-organization we can understand simply by a system undergoing variation, and that variation can be deterministic or indeterministic, can be ordered or random, but variation sooner or later tends to end up in a stable configuration, which we call the attractor. In the attractor, the system is constrained. It has lost degrees of freedom. That implies that the components now are coupled. The components are no longer free to move independently. And it's precisely these couplings that produce the new input-output relations that we defined as emergent properties. So the whole conclusion is emergence to self-organization is a simple process. It's a common process. We see it everywhere in nature and in society, and it's a natural process. That's what my main message. You don't need any mystical or supernatural explanations for emergence.